Me first share the screen. Yeah. All right. So thanks, Prabal, for having me here. Yes. So Prabal already introduced me. I'm based in Belgium, and I'll be speaking about chemical diversity in rocky exoplanet interiors and interior atmosphere interactions. So my research interest really lies in understanding how exoplanetary rocky interiors can change the atmospheric chemistry. And not only that, but how they can change other observable parameters like mass, radius, and things like this. So my motivation comes from that direction. So in this talk today, I will give you an overview of what I think where the field is going. And I'm really excited with upcoming facilities that we are really now close to studying smaller planets in detail. All right. So yeah, this we already know. There are now so many planets. So I would like to start with this histogram, which is not corrected for observational bias. And I would really like to start with the dotted line here. So this is what we knew 12 years ago. So you can see very small population of small exoplanets. So these are the small exoplanets for me, and these are the big exoplanets. So very small population, but then thanks to Kepler mission, we really had these two peaks of small exoplanets. And then suddenly we started seeing that population of small exoplanets is much bigger. And of course, over 10 years, then we knew that small exoplanets are ubiquitous, and the dichotomy between these two small planet population exists. So in some sense, just by looking at this histogram, exoplanets could be divided into obviously small and large. They are separated by, one can call this as a sub-Saturn desert. And within the small planet population, there could be further separated by something called radius valley. So just based on this, then we get these three types of planets. So rocky planets are mostly rock, that's obvious. Sub-Neptunes then contain both rock and gas. And this is very interesting. And gas giants are mostly gas. And because sub-Neptunes contain rock and gas, they can have quite a span in mass radius relations, which I'll show in the next slide. But before that, let's take a look at a histogram, which is corrected for observational bias to a certain extent. And what we see here, the radius valley now looks much more clear compared to the previous histogram. And of course, the population of gas giants is not as much as you would think from the previous plot. So this is obviously because we, as observational techniques favor detecting larger planets than smaller planets. But what is also interesting about this plot is there are two lines you see. One of them is young planets. So young planets have a smaller population of at least these super Earths compared to some Neptunes. But the old planets have almost the same population. So this is also, in some sense, indirect evidence of sub-Neptunes are turning into super Earths as a course of evolution by losing their atmospheres. Of course, I won't go into details into the effects behind this, but this already tells us we are in the characterization era of small exoplanets with the help of James Webb and also VLTI. But also now in the future, we are getting newer and newer instruments. And this is, of course, not a complete list, but these are some of the instruments which will characterize either the radius of the planets or also masses. And MARVEL is such an instrument which we are building at University of Leuven, where one can measure the minimum masses of exoplanets. And at the ELT will be able to do much more things than one could imagine. And of course, there is also aerial mission of ESA, and this will also characterize small planets, especially sub-Neptunes. There are also some concept missions. I guess Habitable Worlds Observatory is being discussed here in the group a lot. There's also Life mission, which is being discussed a lot in the community now. But this is all very exciting for me as a person who does modeling or lab experiments. So there's plenty of data going to come to test our theories. So this is one of the way I try to identify what is the potential extent of chemical diversity of exoplanets. And one of them is measurements of their masses and radii, which give their bulk densities and thereby the bulk composition. And again, what I've done is use the previous histograms to divide the population into three types: rocky planets, sub-Neptunes, and gas giants. And what you can see here is rocky planets follow closely to the rocky sphere line. So these all mass radius relations are idealized circumstances, just assuming planets made of rock, water, hydrogen, or iron. And you can see that rocky planets are very close to the rocky line. Sub-Neptunes all the way extend from rocky here to somewhere in between hydrogen and water line. But then gas giants are very close to the hydrogen line. So that's what I meant when I said that rocky planets are mostly rocky, gaseous planets are mostly gassy, but sub-Neptunes are really in between, and they potentially can have quite a diversity of compositions. And of course, another direct window is atmospheric chemistry, which is now possible with transmission and emission spectroscopy. And this is just a figure from a few years ago, which shows how JWST will drastically improve our understanding of atmospheric chemistry. And of course, in the past year, there have been many studies now which actually show JWST is working really great, and we can achieve a lot more with atmospheric chemistry. But one of the less talked about windows I like to think of is the interior chemistry. By that, I mean rocky interior chemistry of planets. And this, I will go a little bit into detail later, but I'll just say here that one of the ideas is refractory elements like iron, silicon, magnesium, they reflect ratios that are similar in the stellar photosphere and planetary interior, because during planet formation, all the material which is refractory comes from the same source of cloud and dust. So basically, these ratios should be mirrored. Although this is not really true, by these points, you can see that sun is here, but Earth falls here. And of course, a lot of planet formation processes can further change these ratios. But in general, these ratios still allow you to study statistically how different the compositions of exoplanets could be. So in principle, there are three windows. One gives you bulk composition, one atmospheric composition, and one interior composition. Of course, there are, this is not an exhaustive list. There are many other indirect ways to infer chemistry. Okay, so I'll also talk about interior atmosphere interactions in this talk, and specifically three types. One is the outgassing from rocky interiors. One is geochemical cycling, and one is gas solubility and magma gas reactions. What I would already argue that knowledge of interior properties is key to understanding the atmospheric composition of exoplanets, especially small exoplanets, where interiors dominate the mass. Thereby, processes like outgassing can really change the composition of atmosphere. So knowing the interior is very important. With this nice graphic, I'll try to show. So this is mostly an extension of what we know for planets in the solar system, rocky planets in the solar system. So in the beginning, when planets are forming, due to chemical segregation of mostly iron alloys, there is something called metal rainout, which starts forming the metallic core of the planet and leaves behind a silicate mantle. And as time progresses, there might be still a nebula present at this stage, and there could be processes like nebular engassing, and this is H2 dominated time or period of planet formation. And beyond that, you would also get core mantle equilibration. And as time would progress, you would expect also the interior and atmosphere. So the core is fully formed now, but the silicates are still in a molten state. So this is what we also call a magma ocean. And the magma ocean or the interior and the atmosphere can equilibrate. And of course, once magma ocean starts crystallizing, there could be more and more outgassing. And in this case, you would expect atmospheres that could be taking different forms. One could be they are simply CO2, H2O dominated atmospheres. There could be slightly reducing atmospheres like CO dominated. But there could be also silicate vaporization, which could lead to completely different atmospheres than the traditional volatile atmospheres. As further the planet evolves, there could be also further evolution in the atmosphere. For example, if geochemical cycling allows the cycling of certain volatiles like CO2, H2O condenses to form an ocean, then you are left with an N2 dominated atmosphere. And further, for example, on Earth, life has altered the atmosphere by producing large amounts of oxygen. And then, of course, oxygen is a big player in the atmospheric chemistry. But yeah, so this is how interior can completely modify the atmosphere depending on its stage of evolution. So this already gives you an idea of diversity you can expect. So now I'll go a little bit deeper into chemical diversity. And first, I will really start from what we know in the solar system. So in the solar system, there is diversity of the metallic core sizes compared to their mantles. And this is what you expect with some inner solar system rocky bodies. So Moon, Mercury, Mars, Earth. So Moon has a very small core compared to its mantle. Earth and Mars have cores which are about 50% in radius fraction, or about a third in core mass fraction. And Mercury has really, really large core. So, but still within the solar system, for the rocky bodies, we expect the core to be made of iron alloys and the mantle to be made of silicates. Now, what we looked into is if you want equations of, so for calculation of interior structure models, you need equations of state, especially the information on density of particular materials. And one of them, which is really relevant, is iron for these calculations. So we looked into it, and at the time, there was limited data on lab experiments. And this would roughly be the central pressure of Earth. But this was also limited due to not only the science goals, but also which facilities you could use to do lab experiments. But then, of course, once you want to calculate this for super Earths, you would expect to go to very high pressures. And these pressures can exceed an order of magnitude beyond the validity range of the data on lab experiments. And that's why we call it like extrapolation here, because there is no data here. What we did instead, of course, you cannot do lab experiments, but then you can do ab initio calculations. And we calculated a density functional theory based equation of state to very high pressures. And we then compared it with the existing equations of state in the literature. And this is the density difference as a function of pressure, roughly follows this. And what you can see at high pressures, there could be as high as 20% difference in the density between the equations of state, because they are different polynomials or different mathematical formulations fitted to data from different sources. So naturally, when you extrapolate them, they are going to give different results. And these differences are with respect to our equation of state. So 0 is what we calculated in our study. So now what is the impact of such density differences in mass radius relations? So this is what we try to show here. And I calculated such a mass radius relations for 4 types of planets, one which are pure iron, one with a Mercury-like core, one with Earth-like core, and Moon-like core. Moon-like core being keeping to pressures much below the Earth's pressure, there are no differences. But as you go to Earth-like planets and Mercury-like planets, you see the differences for a given radius in mass could be as much as 20%. So of course, knowledge of correct equation of state is very important in these kinds of studies. And of course, now we are, so this is old data from 2018, but now the mass and radius constraints are much better than 6 years ago. So that's why this is even more important to use good equations of state. I would also like to mention that thankfully now there are more and more experiments coming up, and these should also be integrated in equations of state. But like I said, what I showed you before was for pure iron. But now one should really use equations of state for iron alloys, because in reality, you would not expect metallic core of pure iron. You would certainly expect some light elements like sulfur, silicon, carbon to go into the core. And that is what we try to also compute here. And of course, these equations of state are, again, extrapolated beyond validity, because at the time there was no data at very high pressures. So what we just try to show here is, let's say, just take a Mercury-like super Earth. We show that compared to pure iron scenario, binary alloy like FES can result in a very low mass, like 35–40% less than what you would expect with pure iron. So of course, this is also something which needs to be accounted for in interior structure models, that the presence of light elements in the iron core. So binary Fe alloys decrease the density of the core up to 20%. But like I said, there is lack of data at extreme pressures and temperatures. So all of this is extrapolation. There are many elements which can go with the core. We call them siderophile, iron-loving elements. But again, we do not know the stability of if you put multiple light elements together at the pressures of super Earths. And this is a field which is now rapidly advancing. So I'm I'll be looking forward to more data on this in the future. And of course, these are important even for study of sub-Neptunes, as mentioned here. And it has been, I think, really good. It is really good that the community is now starting to use or consider the presence of light elements in the core. Okay, so coming back to the star-planet connection or the chemical diversity of rocky interiors. So I think I said most of this, that the relative elemental abundances of especially elements like iron, magnesium, which form most of the rocky interior, are expected to be mirrored between the rocky interiors and the stellar photospheres. And in this figure, you see there are differences between the sun and stars. But what you also see, there is a sufficient diversity in these compositions. So in principle, to quantify the diversity in chemistry, such information can be used either in a statistical way or just used as a proxy corrected for certain trends. For example, the Earth-Sun differences. So this is one way to look at this. And why this is important? Because as soon as let's take a look here at here. So for a planet with iron alloy core, a silicate and water ice. So this has also been theoretical discussion on these planets existing. And if you add a third layer, then the interior structure calculation based on mass radius becomes degenerate. And this is what is highlighted in this figure as a function of ice mass fraction. One can assume different core mass fractions. And this is for a planet with exactly the same mass and radius. So you could construct different interiors. So you need something else now. And one of the ideas proposed is to use stellar elemental abundances of refractory elements. That's what I showed, combined with mass and radius. And this would give a little better understanding of what kind of compositions one can expect. This is what we showed here. These elemental abundances are also important in the interior thermal state. And in this figure, I would like you to just focus on the different colors here. So in the blue, what it shows is if there is a planet with composition, mantle composition, following this much of FeO content, this much of MgO content, and this much of SiO2 content, you would expect a single layer convection. But if you go in the red zone, you would expect a double layer convection. And this is because there would be density segregation because of the peculiar mantle mineralogy you would expect. And this would mean that the convection in the upper part of the planet would be completely scaled differently compared to Earth. And this has, I think, quite important implications. Another way to look at mantle mineralogy is something which is called partial melting. And this is really important for volcanism. And what you see in this figure, I would just like you to focus on these two lines, the purple one and this one. And the differences between these two lines imply that as you go deeper, so this is pressure, so you go deeper in the planet, you would expect melting at different temperatures. And this would mean if, let's say, the temperature is very well known, or one can predict the temperature somehow. I don't know how exactly, but let's say if the temperature is predicted to be around this, so one would expect there is much more melting in this case compared to this case. And that is completely a function. These two cases are a function of these refractory element ratios like calcium to aluminum and magnesium to silicon. So there is also a lot of connection to outgassing with respect to chemical diversity in mantle. Now I'll go a little bit in a different direction. So here in this figure, what you see is magnesium to silicon ratio as a function of carbon to oxygen ratio. Normally, carbon to oxygen ratio is a volatile ratio, and it does not, I mean, it plays an important role for during planet formation and also atmospheric chemistry. But for solids, because carbon largely stays volatile, so this is sun here for reference, carbon largely stays volatile, and that's why it does not it is not contained in large amounts in Earth or Mars, compared to what you would expect by theoretical models in the right side of the diagram. So these two blocks, so one is carbon to oxygen greater than 0.65 and one is 0.8. In these two blocks, you would see that carbon precipitates as carbides and graphite in large amounts in the protoplanetary disks. And N-body simulations of such disks have shown that you could get more than 10 weight% of refractory carbon in rocky planets in this region of parameter space. And this is really important because once formed in these conditions in large amounts, carbon is very difficult to get rid of. And that means it will be an essential building block of rocky planets. So then the question arises, what is the mineralogy, structure, and evolution of such carbon-rich rocky exoplanets? And this is what I tried to study from different ways. One of the ways I looked into is performing high pressure, high temperature experiments. And how you perform these experiments is you start with certain synthetic powders, you mix them well and contain them in effectively a furnace, a small mini furnace, which can sit in a machine like this high pressure machine you see. So this can really compress this setup to pressures which mimic planetary interiors. And once this experiment is performed, you can analyze your experimental run products with an electron microprobe. And this is a cross section of such an experimental run product you see here. And the scale is really small, so it's 10 micrometers. So we are really zooming in. And what you see in different colors are different phases. These are performed at high pressures. So they represent probably pressures equivalent to deep interior of moon. But for Earth, these pressures are not really high pressures. So you would, for simulating Earth-like planets, you would need to go even at very deep, different machines, so which can produce these pressures. But what you see in different colors is different phases which are geochemically stable at these pressures. So you see olivine crystals, there is some molten silicate, then there are iron alloys. All these are stable at these pressures and temperatures. But you also see graphite here. And this is because whatever carbon that could be absorbed in molten silicates or molten iron alloys is absorbed, and whatever left is just in the form of graphite. And what is important to know here is all these different phases can have different densities. And due to different densities, you would get gravitational segregation in a real planet. And this is what leads to things like metal rainout in planet, that because iron is twice as dense as silicates, and then of course it rains out to the deep interior and forms the core. Similarly, graphite is very low in density. So it will form a flotation layer on top of a silicate magma ocean. And then in that case, you would get a 3-layered planet like this with a metallic core, silicate mantle, and a graphite lid. Then the question is, what happens to the interior structure of these planets? So now I'm showing a lot here, but what I would like you to focus on as you go on the horizontal axis on both these plots, the graphite weight percent is increasing. And these are the interior structures of these planets, where from the surface to the interior you go, you see there are transitions. So this black region, here, this black region is graphite, then there is silicates, and then there is iron. So based on such calculations for a given size of a planet, sort of fixed size of a planet, you can compute the mass. And that's what I do here for two cases, one assuming a pure iron core, one assuming a FES core. And you see that the mass could be quite different given the amount of graphite. So as you go from 0 to 28% graphite, you already see a difference of several percent in mass. And these are some of the things which are noticeable now. So, sorry, I think I got a question. Shall I address questions now or towards the end?
You can do whatever you'd like, Kaustubh.
Okay. I think I'll address them towards the end. But please write the questions there so I can go through them later. So, of course, for a large planet, what will happen is graphite may not be stable in graphite form. It might form diamond, because about around 5 GPa, gigapascals, or 50 kilobars, graphite changes into diamond. And diamond has a density similar to silicates. So although it might be a chemically separate phase in the planetary interior, but it might not be able to gravitationally segregate. So it might form a silicate diamond mixed mantle instead of a graphite crust. So both options are possible simultaneously as well, or one can happen at a time, depends on equilibrium, pressure, temperature conditions for whatever planet you might think of. But especially for larger ones, forming diamond is very likely. But for one case, what I discussed, I tried to calculate for planets with a graphite outer shell. And this would be true for smaller planets. And what I tried to compute here, as a function of the thickness of the graphite lid or silicate lid, I tried to compute a duration of convective cooling. So this means for how long the mantle goes on in solid state convection. So for silicate planets, it can go up to several billion years. And this is for, again, I think Mars-sized planets. So this obviously, that's why it goes out in a few billion years. Otherwise, it will be even longer. But for graphite-lit planets, this is less than 200 million years, or about 300 million years. And this means that from a planet evolution standpoint, you would expect, because of the presence of graphite, you very efficiently lose the heat of the planet. And this, what I found was this can cool the planet up to 10 times faster. And another scenario which I was discussing is nicely compiled here, is again, on the horizontal axis, you have the time evolution, and on the vertical axis, you have something called Rayleigh number. So Rayleigh number is a quantity which tells you if you are in a solid state convection or not, effectively. So of course, it has a deeper meaning, but the reference is this Rayleigh critical number. So if you are above that, you are in a solid state convection. And if you are around it or below it, you are in a sluggish mode and even reach a stagnant mode. And what this means is, you have, in the blue cases, you have efficiently lost heat. So now the convection is not as vigorous as you would expect for an Earth-like planet. And of course, both these effects are because of high thermal conductivities of graphite and diamond. So material properties, knowledge of material properties is very important. If you have a planet which has different materials, it can really change how the thermal evolution works. And in both these cases, what is clear is you lose heat of the planet, formation heat very fast. So one can also argue that evolved carbon-rich planets are potentially less volcanic, given these calculations. So another point I tried to study is how silicon carbide layer can interact with carbon-rich planets. This is because for carbon-rich planets, in the protoplanetary disk, you also get lots of silicon carbide. But it is known to be unstable at nominal redox conditions, and I wanted to study how it is consumed. And that's why I designed an experiment where a silicon carbide layer was touching a carbon-rich planetary layer, and we tried to look this into detail. And this is the reaction zone in green. So there's a lot of things going on here, but on the top, you see silicon carbide reacting with the, you can consider as silicate magma and forming a lot of different stuff. And all this stuff like iron sulfide, iron silicide, graphite, quartz is all a result of the reaction between silicon carbide and the silicate magma. So effectively, one can write down a chemical reaction from an experiment like this, where silicon carbide reacts with iron oxide to form quartz, iron silicide, and graphite. So this is the way the reaction is consumed. So what you see mostly is a reduction of Fe2 plus to Fe0 or metallic ion. And this is important also potentially for future observations, because if one can find a method to sufficiently well detect the surface of a planet where you can identify the iron 2 plus on the surface. So at least in this idealistic scenario, it would mean if you find Fe2 plus on the surface, it's very hard to have a silicon carbide in the interior. So to close the chapter on chemical diversity, I would convey the message that we should not just think about solar terrestrial rocky planets with iron alloy and a silicate mantle. There are a lot of possibilities, and different materials can have different effects on the interior evolution and thereby also atmospheric chemistry and potentially mass and radius of these planets. So how am I doing on time, Prabal?
So I'd say you probably have another 10 minutes, maybe max 15.
Okay. So let's go to interior atmosphere interactions. So first is outgassing. And in outgassing, what I would like to first discuss is briefly about oxygen fugacity, because we hear this term a lot. So oxygen fugacity is nothing but a partial pressure of oxygen corrected for its real gas behavior. In geochemistry, oxygen fugacity is a very useful parameter because just if you take Earth by mole percentage, about 50% of moles forming planet Earth are oxygen. So obviously oxygen is a main, although it's a volatile, it's considered to be a volatile element, it's a main role player for defining the interior of the planet. So the oxygen content of the planet is effectively correlated with oxygen fugacity. So what is also, it's very important because the outgassing of different species would depend on the oxygen fugacity of the mantle. And this, especially for magma ocean outgassing, this is also a very important effect because you have direct interior atmosphere coupling at that time between the magma and the atmosphere. And again, this would also drive the chemistry of the atmosphere close to the surface, because these chemical reactions would be effectively a function of oxygen fugacity of the mantle. So one of the ways to define oxygen fugacity is to take something called a buffer. So in this case, the reaction happens between metallic iron, oxygen gas, and it produces iron oxide, which is also called Wüstheit. So this iron Wüstheit buffer effectively is a very good proxy for a given system to have your oxygen fugacity computed or measured with respect to this buffer. So this probably is clear, better clear from this figure. So in this figure, what you see, oxygen fugacity, the logarithm of oxygen fugacity as a function of temperature. And this blue line is the iron Wüstheit buffer. So as you go to different temperatures, the chemical equilibrium of this reaction, this tells us that the oxygen fugacity would increase as a function of temperature. So now when talks about oxygen fugacity, one can do a delta notation with respect to this iron Wüstheit. And that's why in geochemical literature, there is a lot of notation, which is delta IW with respect to curves like this. But now, of course, depending on the system, how oxidized or reduced it is, you can move to another buffer. And this is possible in this diagram. I won't go into details further on this. But this I'm telling because this particular study led by Dan here shows that for different melt fraction of the planet, you get different composition in the atmosphere. And this is largely due to the solubility of different gases in the interior. And different gases are soluble to different extent. So this is a busy figure, but I'll start with this. In this figure, what you see, mostly carbon monoxide is present, and then there is also some carbon dioxide. And the total pressure is given here. And this 1% H means that only about 1% of hydrogen is in the atmosphere, given its total budget. 99% is in the interior. And as the magma ocean crystallizes, you get more and more hydrogen in the atmosphere. And that's why this blue region, which is water, increases, or steam rather, is increasing here. So in a classical understanding of early atmosphere of Earth or Earth-like planets, the idea is you go through a process called fractional crystallization of the magma ocean, where you completely solidify magma ocean and everything or close to full solidification. But then most of the dissolved species are now part of the atmosphere. And that's why you classically get things like a steam atmosphere. Most of the atmosphere is steam. But in this study, we showed that at about 30% melt, you would rather get a carbon monoxide dominated atmosphere, or in general, carbon dominated, carbon bearing atmospheres. And this is because at this melt transition, the rheology of mantle is such that it moves from a very vigorous convection to a sluggish convection mode. And this creates a surface lid, which then in some sense delays rest of the outgassing processes of magma ocean crystallization. So in some sense, this has very important implications on the formation of surface water oceans, for example, because this will delay the outgassing of steam and then condensation of steam onto the atmosphere. And now I'll show you the effect of oxygen fugacity. So in this particular case, I repeated what we saw in the middle plot in the previous one, but then you can go to a reduced melt percentage. And what you see here is at this reduced weight, reduced oxygen fugacity, you get mostly a carbon monoxide rich atmosphere, even more than in this case. And for a higher oxygen fugacity, you get a carbon dioxide atmosphere in this case. But nevertheless, early atmosphere seem to be carbon bearing molecules with carbon bearing molecules. So these are carbon dominated atmospheres. So they might be very common. Now, of course, there are plenty of effects, and a lot of studies have been going on to look into these specific details as a function of oxygen fugacity, but also the pressure, the surface pressure. And you can see a variety of atmosphere. I won't go into detail, but there's a lot of important literature out there on this topic. There are a couple of more topics. So I'll just mention this very quickly. So in terms of carbon silicate cycling, so this is a geochemical cycle which captures CO2 from the atmosphere into the interior and then recycles it back to the atmosphere. So in this particular case, what we tried to study is a process called silicate weathering. So where rocks on the surface react with H2O and CO2 and produce carbonate minerals that are subducted, that are transported to oceans and then eventually subducted. So for this particular case, we applied a 3-regime weathering model. And this model, we really show that it is important to use these kinds of models because most of the previous work in exoplanet literature considers kinetic regime of weathering, but there could be different regimes, which the two of them we explore in the study I'll show is thermodynamic and supply limited weathering. And what we find here that as a function of surface temperature, weathering rate shifts from the kinetic regime of weathering to the thermodynamic regime of weathering. So this is a very important turnover because in the kinetic regime of weathering, you expect negative feedback. But in the thermodynamic regime, then you would expect a positive feedback. So this has important implications on the stability of habitable zone. And this is what which is not studied yet, and this needs to be also studied in the future. What is this? What is the impact of this positive feedback? Okay, so I have I'll skip some of the slides and directly jump to my conclusions, where I tried to argue in this talk, and I hope I convinced you that rocky interiors are likely chemically diverse, much more diverse than what we normally think of in terms of Earth. And chemically diverse interiors then are subjected to extreme pressures and temperatures, and we have very limited data. And all these models for interior structure, thermal evolution, they use some data or other, and most of the times there is requirement for extrapolations. So what we really need in the community is a lot of ab initio calculations for not only Earth-like scenarios, but chemically diverse scenarios and also high pressure temperature experiments. And these models really need to go beyond the physical and chemical ranges of Earth. And I think the community is trying to go there, but we need to do much more. And these chemically diverse interiors are very important in controlling how the atmospheres of small exoplanets will be, chemically, also physically. And that's why interior atmosphere coupled models should be used. And I see that happening a bit more now compared to several years ago. And of course, in the future, then it will be great to incorporate the effect of interiors on a lot of observable atmosphere physics and chemistry, which includes photochemistry, radiative transfer, GCMs, and a lot more. So I'll just stop here and leave at this point.
Thank you, Kaustubh. Really interesting talk and covering everything from interiors to kind of the effects on the atmospheres here, huh? So I'm going to open this to questions. I know we already had one. Joe, do you want to unmute yourself and ask?
Good. Okay, Brubble and I are in the same room, so we might get some feedback there. Great talk. Awesome work that you're doing. So yeah, I threw a question in there, just a quick one about one of the figures you showed earlier on that was looking at the carbon-rich planet for a pure iron core versus a core that had sulfur in it. I was just curious how much sulfur you looked at. I think it was like slide 16 or something like that.
Yes. Yeah.
Yeah, so I was
Thanks
just
for the
curious how
question.
much sulfur was in that
Yes.
model.
So here I really went for the extreme case of 50 mole% of sulfur.
Okay. Sounds good.
So FES literally means Fe 0.5 S 0.5. So same.
Cool. And then kind of a question just about any work that you've done or that you've seen or your team has done, you know, with these diverse chemical interiors. I'm really glad that you're highlighting the importance of this when it comes to density and the potential for outgassing. But I'm really curious about if viscoelastic parameters are being measured for any of these materials, particularly at these high pressures. So things like viscosity or rigidity or bulk modulus, any of those?
Yeah. So yeah, you actually asked a very, very important question, which I also always try to look up in the literature. The thing is, lab experiments are different for every measurement. So every type of measurement, you need to look into different devices and people from different communities even. And especially for simply properties like thermal conductivity, this is not done in the type of setups I would do my lab experiments, because these are just high pressure, high temperature geochemical experiments. So for this, we sometimes try to reach out to some of the authors who have published before and ask them, are there any updates? Because sometimes, like mostly, I think the lab community which has gotten together in planetary science, I see the most involvement from high pressure, high temperature lab side. So these are often called experimental petrology labs. And these are the ones who get involved the most. So now they are direct contributors to this science. But measurements of other properties, thermoelastic properties, they are still being done by somebody, some of the labs which have industry applications. So they do most of the calculations at 1 bar and things like this. So for some of the properties, it's very difficult to find any data. And sometimes for them, also, it's not relevant to go to high pressures, or sometimes they are also limited because they have never thought of setups which go to high pressures and can still measure properties. But yeah, so this is also something we think about a lot. But again, yeah, you do what you can.
Yeah, for sure. Awesome. Thank you. Well, awesome work and great talk.
Thank you.
Any other questions? So nobody has a question right now. I'll actually ask an additional one. So Kaustubh, you were talking about kind of the difference between the graphite versus kind of diamond convective interiors. I guess this is based upon size. Is there a particular limit at which you can say, hey, this would inhibit or is likely to inhibit outgassing to the extent that it's visible in volcanism?
Yeah, so you're talking about really thick graphite layer, right?
Exactly.
Yeah, so this is something I gave a lot of thought, but did not really find the right ways to implement any models. So graphite in a lab is quite different from graphite in reality. So for example, just think of like the graphite lead pencils, no? So these kinds of graphite materials, they are very porous. I mean, they are the ones, the lead pencils, which we use, we call them like that. They are still compressed, so they are still okay. But when you look into some of the graphite material, which is naturally stable, it comes with even up to 30% porosity. Now, what happens at these conditions, because of high porosity, graphite is also very brittle. And one of the ideas could be because of having a really brittle nature of graphite. Even if you form, I don't know, really thick layer of graphite, but it could be still breakable in some sense, literally. You could have simple like permeability through it. You can still have possibly volcanism through it. So it really depends on how thick the layer is. If you form a really thick enough layer to form diamonds at the bottom, maybe it could mean something else for the evolution of the planet. Maybe then, but still what we find is eventually the volcanism, I think, will be limited by how efficiently heat is lost through the planet. And one thing graphite and diamond are good at is letting the heat out of the planet. So, so it's really, one needs to do a full calculation and understand what it means to be in terms of can you really form something like a graphite continent on a top of a silicate magma? So this is something one needs to really put down a model for this.
Sounds like a good future direction, research directions for something, right? So, not bad. So thank you so much, Kaustubh. We're right at noon here, so everybody, please thank Kaustubh for a really interesting talk. I think it's promoted and provoked a lot of thought about kind of how exactly planets might evolve and what their structure might be. And Kaustubh, I assume that if people have questions, they can send you an email.
Yeah, absolutely. Feel free to send me emails. And I think yeah, it's really nice to be discussing things here. And I also try to minimize anything about atmospheres, just to, because I know in this group I think there is a lot of already knowledge about atmospheres, so I cannot share much. So I tried my best from the interior side. Hopefully it motivated people to think more about interiors.
Absolutely. Thanks, Kaustubh. One last thing. We have this recorded, and I'm sure people will want to watch this too. Are you okay if we post this to the Exoplanet Seminar website?
Yeah, sure. That
Awesome.
works for me.
All right. Well, thank you so much again, Kaustubh, and everybody have a great day.
Thank you. Bye-bye.